Welcome protein coders, let's build some coding muscles. Today we're gonna see Dijkstra using priority queue. But why priority queue? Let's go back to our previous lecture and revise a little bit. So what we are doing is we are starting from our source node. In this graph we started from 0, right? Then we explored the neighboring nodes, and then from our distance vector we updated the distances. Then we chose the shortest distance node, right? We are finding the shortest distance node, and then we will move to this node and we'll mark it as explored, right? And from that node again we will explore the another unexplored nodes, and we are repeating this process n number of times, or v number of times, the number of nodes present in our graph, right? So here we were running a for loop from 0 to number of nodes, right, to get the shortest distance in a distance vector, and then we are performing all these three steps v number of times. So our time complexity will be order of v square, which is very high, right? So that's why we will use our priority queue to find the shortest distance node. Okay, so because we are finding the shortest distance node, right, we are comparing the distances. So in our priority queue also we will push distance and node. Distance will be our first parameter, and we will use min-heap. And because we use min-heap, our time to find the shortest distance node will be order of log, okay, logarithmic order, log of e. So now we know why we are using priority queue, to get the shortest distance node in order of log time complexity. Okay, now let's see our algorithm. What we're going to do is get the shortest distance node from the priority queue, again mark it as explored, and then relax the edges, and at the end, after relaxing edges, push the relaxed node with distance into the priority queue. And if you see carefully, earlier also in yesterday's video also we did the same thing in our normal Dijkstra also, right? That we found the shortest distance node, mark it as explored, and then while exploring, relaxing the edges. Same thing, okay, just with the better time complexity. Let's see in the code. We have our node, number of nodes, source node, and adjacency list. So let's first create our explode vector and mark it as 0, all nodes, and then our distance vector initially initialize with int max, and we'll mark the distance of source node to be 0. Because we're gonna have the pair of distance comma node, so let's declare our pair int comma int as pii, so it will be easy to declare a min-heap. So let's declare a min-heap priority queue pii, vector of pii and greater of pii. Let's call it p, and let's push the initial source node with distance 0 in the min-heap. We are pushing distance and node. Okay, now let's start our traversal. Why our priority queue is not empty? So what we'll do, first we'll get the node, okay, from the priority queue, and we will pop it. Then we will check if it is explored. If the node is already explored, then we will continue, we will not process, else we will mark it explode. Okay, now we will traverse for its neighbors. Okay, first we'll get the neighboring node, and then we will get the distance of that neighboring node, edge weight, and we'll check if the neighboring node is not explored and distance of neighboring node is greater than the distance of node plus edge weight, then we will update this or relax this node, right? So we'll update the distance of neighbor as well as push this neighboring node distance and neighboring node into our priority queue. And that's it, guys. At the end we will return the distance vector, and that's it. In our normal Dijkstra we just use priority queue to optimize it. Now let's revise what we studied. We first studied why we use priority queue, why we need priority queue, right? Then we saw the algorithm, which is similar to our simple Dijkstra, right? We'll get the shortest distance node, mark it explode, and relax the edges. Now if I want to share something, suppose we have a priority queue, right? So in our priority queue, the approximate number of the values we can have is approximately equals to the number of edges, right? So because it's a min-heap, so the time to push the element and pop the element will be order of log e, and for e edges it will be e log e for pushing and e log e for popping out elements in worst case. So it's nearly equals to e log e. okay, which is better than v square in case of sparse graph. Okay, pop notes for log e. Yes, so in case of sparse graph it is better, e log e. Okay, then we saw the code for it, right? It's very similar to our previous Dijkstra, simple Dijkstra. We'll have our explode vector, distance vector. We will mark distance of source as 0. Then we initialized our min heap, push the source node and its distance 0 into it. Then while priority queue is not empty, we got the node, we will pop it out, right? We will check if it is explode, we will continue. If it's not explode, we will mark it explode, and then we will relax the neighboring edges for it, right? We'll get the neighboring node, its distance, and check if it is not explode and neighboring node distance is greater than the distance of node plus edge weight. We will relax it and push it into the priority queue, and at the end we will return distance vector. So that's it from my side, guys. If you have any questions, please mention them into comment box. You will find the problem and solution link into the description box. If you don't understand, don't like, don't subscribe, but if you do, please show some support. Keep practicing, keep smiling. Thank you.